All right, so we're going to be basing a lot of our examples today off of the homework packet. If you don't have the homework packet, you can download it from the Haiku page there. It'll be there. You can pause this video. You guys can pause it and copy this down, so go for it. So this describes here how two polygons or two shapes are similar. So you have to meet two conditions here. You got to meet the first condition, which says that all of your matching angles have to be congruent. In which case, if you look at these two figures down below here, I've got this first angle up in the let's look at this here. Whoops. In the upper left-hand corner matches this. You've got this second angle matches this. This third angle matches this, and so on. All the way around there. So I've established that. Then the second part, in order for them to be similar, the corresponding or matching sides have to be in proportion to each other. So if we take a look at the proportions, like you take a look at this first one, the 2, this side length matches with this. You could do 2 over 6, or you could reverse it. You could do 6 over 2, doesn't matter. So if I do 2 over 6 and then I go to the next one, that's 4 over 12. 4 over 12, which is, if I reverse that, that'd be 12 over 4, and then just go all the way around. 8 over 24, 8 over 24, or conversely, you could do 24 over 8, 3 over 9, or the reverse of that, 9 over 3, and then you got 1 over 3, or 3 over 1. As long as these ratios are all equal to each other all the way around, which they all are, because if you could reduce all of these fractions, they would all equal 1/3. So then you would say that you've satisfied the second condition right here, that the corresponding sides are in proportion or proportional to each other. And same thing goes here on the bottom. So we would say that the ratio of the side lengths is called the scale factor. In the top answer here, we all got, for all of these, they all reduced to 1/3. So the scale factor was 1/3, or you could write it this way. You could write it as 1 to 3, which says the same thing as 1/3. If we look at it from the perspective of the bottom, then the scale factor would be not 1 to 3, but 3 to 1. So it just depends on how you look at it, like which side length that you put on the top. Okay, so did we go small to big? If we went small to big, then we went 1 to 3. If we went big to small, then we went 3 to 1. All right, so now let's apply this to triangles. So you can pause the video there and you can copy this down here. Okay, so just one recap back to this. A couple questions were asked. Which one do you use? Do you use 1 to 3 or do you use 3 to 1? They will ask you, they will tell you which one to do. They'll say, okay, the small one to the large one, then you do 1 to 3. If they say, well, tell me the scale factor of the large to the small, then you do 3 to 1. And then another question was asked, do you use the colon notation or can you use the fraction? I typically use the fraction, but I just wanted to kind of throw that one at you. Sometimes you will see it in that format as well. All right, let's take a look at these down here, down below. You can tell whether or not two triangles are similar as long as two angles of one triangle are congruent to two angles of another triangle. So if I have two triangles here, let's say I got a small triangle and then I got a large triangle. These triangles will be similar as long as I'll just do a couple angles. One angle there, and then a second angle here and a second angle here. I know now that these two triangles are similar. It's just a shortcut. Okay, now, the cool thing is if you know that they're similar, then what do we know about the side lengths? They are what, everybody? Not same, but they're in proportion. So that side length, this first side length divided by this side length is equivalent to this side length over this side length, which is also equivalent to this one over this one. Okay? Now, you may never have seen this little squiggly right here. That squiggly means similarity. So it's just an abbreviated form of writing that. Okay, looking at the second one. So we got the first one down. Second one, side, side, side. Now you may recall from triangle congruence, remember all those ways to prove triangles congruent. You got side, angle, side, you got side, 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 you've got angle, side, angle, you've got angle, angle, side, and then you had HL. And HL, remember, was only for a right triangle. Well, if you notice here, you got side, 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 and side, angle, side, and then you see these over here. Side, 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 and side, angle, side. These are not the same. Not the same. They don't mean the same exact thing. Okay, they may actually mean something entirely different. So let's take a look at what they mean. And let's actually use examples to do that. So we're going to scroll down there and we're going to demonstrate that with the next example. There we go. There's a perfect one right there. So copy that one down, and actually this one is number 4 in your worksheet. So if you can either write it on your notes or and then transfer the answer to your worksheet, that'd be great, or just write it directly on your worksheet. That way you don't have to go back and do it later. Okay, so we take this first one right here. The first thing that I want to note is that these angles right in here are vertical angles. So I definitely have that. I don't know any other angles. So if I check up above here, when I look at the 3 ways to prove 2 triangles similar, I can definitely get rid of this one because I don't have 2 angles within my triangles. So that one's out. So it's either going to be side, side, side similarity, or it's going to be side, angle, side similarity. Now I go down here and I look, and I try to make proportions out of these. So in other words, if these side lengths, if these triangles are similar, then their side lengths will have to be in proportion. So if I look at my 6, I've got the 6 down here. Take a look at the other triangle. What side length does that match with? Does it match with the 9, or does it match with the 18? How do we know the 9? True, it's on the bottom, but also, well, not necessarily because it shares the same line. This may sound very elementary to you, but look between these 2 numbers, the 6 and the 12. Obviously, the 6 is smaller, right? So if you look at the other triangle, the smaller of the 2 numbers is 9. So that's how you know. I mean, that's, whoa, what happened here? No, we don't want to change the color scheme. What is that? So that's how you know the 6 matches with the 9. Crazy, huh? Okay, you thought it was like rocket science, but it's really not. Okay, so we're asking ourselves, does 6 over 9 equal 12 over 18? Or, if you wanted to reverse that, we went small to big, didn't we? You could ask yourself, does 9 over 6, does that equal 18 over 12? It doesn't matter which way you do this. You can reverse that. You can do small over large, or you could do large divided by small. Okay, questions there? Lovely. So now you just ask yourself, does that equal? I don't know. Well, let's reduce these. 6 over 9 reduces to 2/3. And then 12 over 18 reduces to 2/3. Hey, it checks out. Yes. And then this is same thing. This turns into 3 over 2 and 3 over 2. That checks out as well. I probably would have just went with this one right here. Okay, so what does that tell me? It tells me that these side lengths, these 2 side lengths in each case, are proportional. I have a personal way that I do this. You're not going to see this in textbooks or anything like that. I put, instead of a congruence, I wouldn't do this, like a congruent signal with a symbol rather with that, because you obviously know that they're not congruent. I put a little squiggly here just to personally note that 6 over 9 and 12, I put a double squiggly. 6 over 9 and then 12 over 18, those were in proportion. Now that allows me to have a nice visual, because if I look at my 2 triangles, how are these triangles similar? By what? Do you guys see it? Side, angle, side. So therefore, this is representative of a side, angle, side similarity. Question? Okay, great question. When you're matching the numbers, why couldn't you match 6 and 12 and 9 over 18 is what you're asking? You could. You actually could. You could take these two sides, you could do small side over the large side of this triangle. Does that equal to the small side over the large side of that triangle? That is actually a third way of doing it, in which case, whoops, 1/2 equals 1/2. The reason that I didn't do that is that a lot of people would say that therefore the scale factor is 1/2, and the scale factor is not 1/2, it's actually either 2 to 3 or 3 to 2. So just be careful, like when you're asked to find the scale factor, it won't tell you the scale factor on that. But it does work. That method works. Question? Great question. Okay, so the question was, if two triangles are congruent, are they similar as well? What do you guys think? Well, let's look at the criteria. You got two criteria, and I was going to go over this, so that was actually perfect. Are the angles congruent? Of course, the matching angles. Automatically, yes. Are the sides in proportion? Yeah, what's the proportion? 1 to 1. So in other words, if this is a 5, and then this one has to be a 5, and like, I don't know, let's say that this is a 4, and that's a 4, then you would definitely have them as 5 over 5 equals 4 over 4, which is 1 to 1. All congruent figures are similar automatically. Okay, so we're not done over here. We got to match up our vertices. We said that these two triangles were similar, L and N. So where are we? L is here, M is here, and N. And what do those match up with? L what? L LTU. Yeah, you got to match up the vertices, how they go. If you do them out of order, you're incorrect. That's the only thing that you should put for the answer. I put side angle side similarity because it says if so, state how they are similar. So you got side angle side similarity, and then you got triangle LTU, and then that would complete the answer. Question over here. Do you have to put the triangle symbol? Yes. Yeah, you don't want to just write the 3 letters, LTU. Okay, great questions. Let's copy the next one down. This is actually number 1 in your worksheet. So let's take a look at this one. First of all, we should recognize that we've got vertical angles here. Let's do green here. Vertical angles. And then also, the mere fact that they gave us parallel lines, you'll probably notice the Z pattern here, which makes alternate interior angles. So this angle will match this one. So how are these similar? These are similar by angle-angle. Angle-angle similarity. If you look at your 3 ways, there's angle-angle, side-side-side, or side-angle-side. This was angle-angle. Now, one quick shortcut. You notice that they gave us no side lengths at all here. So as soon as they give you no side lengths, you can eliminate two of them. Okay, this computer is really on my nerves today. Do you want to change the color scheme to improve performance? No, we don't. How do you do that? Where? Right here? Right here? Oh, I didn't even read. Probably helps to read, huh? Okay, there we go. So it's not going to annoy me again. All right. Lovely. See, what would I do without you guys? I would be on a beach somewhere. Let's see. We've got angle-angle similarity. We said that since they didn't give us any side lengths, it can't be SSS similarity because that uses side lengths, and also SAS uses side lengths as well. So you can get rid of those and just try immediately to look at angle-angle. That's my little shortcut method there. If there's no numbers, you got it. Assume that it might be AA, and then you just got to test whether or not it is. All right, so let's match up our vertices. Triangle LKJ is similar to triangle LBC. Long Beach City. All right. Let's go down to number 18. So you can copy that one. All right, so you may notice in this one, this is actually a very classic example of similar triangles. You will see this a lot. You'll see a triangle within a triangle, and then you'll have this little parallel line right in here. If you notice here, I'm just going to redraw these triangles here, so I'm going to write them off to the side here. So I've got a D up there, I've got an M here, here's a little triangle, and an L. And then the large triangle that it fits inside of is going to be a D, an F here, two grades that you want to avoid, and then you've got E over on the right. There we go. So I've redrawn them, small triangle, big triangle. We're going to see whether or not those are similar. So if I go to my original figure, I look at angle D. Isn't angle D congruent to itself? Yes. It's just like when you look in the mirror, don't you see yourself? If you see something else, you need to talk to us and let us know. Angle D is congruent to itself. Look over at these separated figures. See angle D? It's congruent to this angle D because they're the same angle. Anything is always congruent to itself. Now let's go back over to here to the original figure. I'm going to extend these parallel lines and I'm going to try to make straight flat lines. Try to make yours as straight and flat as mine. Good Lord. You know, like in kindergarten where you learn to color inside the lines and all that stuff? Completely failed that. They passed me anyway. It was... Alright, so we go to here. I know that these lines are parallel. Here is my transversal. I've just highlighted that. And you notice these two angles? What kind of angles are these? They are corresponding. Let's transfer that over to here. So this one, if you notice, this is angle M. So I'm going to put two curvies on angle M. This angle right down here is angle F. So put two curvies on angle F. Do you guys see it now? Yeah, these are similar by angle. You could have just looked at the... Yeah, you could have. You're absolutely. You could have just looked at it. Some people can't see it, though. So that's why I just kind of separated it for you. Just like when somebody's driving and some people can't see you in the crosswalk and it's very painful. So you got angle similarity. Yes, those are similar. So we would say the triangle DEF is similar to triangle DLM, which stands for, don't you love math? Yeah. You know it. What? Don't love math? No. All right, here we go. Let's move on down. Number 22. All right, so we got to find the missing length. They are telling us that the triangles are already similar. So they're saying the angles are congruent and the sides are what? Proportional. Sides are proportional. Okay, so we know that these side lengths have to be proportional. We don't have to prove that the triangles are similar at all. We can just make proportions. So we're going to set up a proportion. We're going to say 4. What does that match up with in the other triangle? Does it match up with the 12 or the 16? Well, gee, it actually is a little bit tricky. So if you take a look at this, I'm going to show you, this is really cheap, but here's how you should look at it. In this first triangle, triangle NTM, is 4 longer or shorter than the question mark? It's longer. So which one is longer in the other triangle? Oh, it must go with the 16. Seriously, I mean, it's that cheap. Okay, it's like shopping at the 99-cent store. All right, so then this question mark, you can just call it a variable, call it x. So we're going to maintain the same thing. So we're going to do 4 over 16 equals x over 12. Like so. The beauty is you can, you guys know cross product, right? You can cross product here, you can multiply. But before I do that, anytime I have a proportion here, I always reduce any fractions that I can. I know that 4 over 16 is 1/4. It just makes my life easier because I don't like to have to, multiply larger numbers or anything like that. So now that reduced, reduce, okay? And then we can do a cross product here. So we can do 12 times 1, which is 12. Copy your equals. 4 times x is 4x. Now I got an equation there, 4x equals 12. Divide both sides of that by 4. You get x is equal to 3. There you have it. Simple as that. Question over here. Great question. Doesn't matter which one you do. Well, you notice that I did small to big. You could actually do 12. You could do 16 over 4. You could reduce it is equal, or not reduce it, but rather reverse it, equals 12 over x. You could definitely do that, and you would get the same thing because 16 over 4 is 4 over 1. And then if you did the cross product, 4 times x is 4x. 1 times 12 equals 12. Divide by 4, you get x is equal to 3. Doesn't matter which way. I usually choose small to big. It's just habit. Okay, let's move on. Let's do the next one. Okay, so once again, we don't have to prove whether or not these triangles are similar. We know that they already are because they told us. So I'm going to separate the triangles. It'll help me to kind of visualize the whole thing. I've got a J there, I've got an A, and I've got a B. JA, it looks like, is 3. JB is 3. And then if I do the large triangle, I got J to L. And JL, they said, was question mark because that's this distance from here to here. So I'll just put an X there instead of a question mark. And then JK, which is that side, is 15. So you can do the same thing. You can just do proportions. You could do, I'm going to go small to big. 3 over x is equal to this side over this side, 3 over 15. And you should pretty much be able to tell what the answer is without having to do cross product, I'm hoping. X equals what? X equals what? You guys are scaring me a little bit here. I don't know. X equals 15. There you go. There it is. Those of you who want to do 3 over 3, 3 over 3 equals x over 15. You can definitely do that as well. And you can tell that x is going to be 15 as well. So it doesn't matter which way that you do that particular one. All right, any questions before we move on? All right, let's move down. Oh, joy. Woo! Look at those notes. You know it. All right, so let us go ahead and pause the video there. You can copy that. Let's see, let's put that back in there. Okay, so basically on this next particular one, you notice here that it seems to be completely unrelated because we don't have, in our figure, we don't have triangles over here. Although if you can kind of imagine that if you were to extend these transversals over here, up into here into a corner, now you would have some triangles. You would have like a triangle here, and then you would have a triangle here, and then of course you would have a middle triangle right in here. Okay, so you can kind of think of it that way, in which if you did have, and those triangles would all be similar to each other, so you could make proportions out of those. But it's much easier just to kind of look at the figure over here on the right. If you notice here, if you have 3 or more parallel lines, which we do, we have 3 parallel lines, and when I say only 3 or more, it's like, well, why did I say that? Meaning you don't have any triangles there or anything like that. All we have is just parallel lines. So I've drawn 3 parallel lines over here, and then I've labeled these little side lengths, like from here down to here. Let's see. From here down to here is A. This distance from here to here is B, and then up here is C, and then right there is D. what you can do, as long as these three lines are parallel, is you can make proportions out of those little side lengths. So we could say that A over B is equal to C over D. So if you do this piece A over this piece B is equal to this piece C over this piece D. That's one proportion that you can make. Another thing that you can do, let's go to the second one. You can do A divided by C equals B over D. So let's look at this. A, so this piece over here divided by this piece on the right equals this piece over this piece on the right. So that's another relationship that you can do. A third one that you can do is you could do B over A equals D over C, which is really, if you look at number 3 is just the reciprocal or the reverse of number 1. I just flip-flop them. So instead of A over B, I just flip that. Instead of C over D, I just flip that, which gives you number 3 right over here. Now the fourth one is a little bit tricky. You could take A, this little piece here, divided by the entire side length right there, which is A plus B. So you could do A over A plus B, and then do the same thing on the right. You could do C divided by C plus D. You could even do more. You could do B over the whole thing, so B over A plus B is equal to D over C plus D. So just lots of different ways that you can do that. What you want to avoid is the following. You cannot do, while you can do A over C is equal to B over D, you can do that. What you can't do is this bottom one right here. That's why I circled it and put a slash through it. You cannot do A over D. Don't do this piece over this piece across over here is equal to B over C. That cannot be done. Or excuse me, A over D is equal to C over B, or the reverse of that, which I forgot to draw in here. You cannot do A over D is equal to B over C. Don't do that. Neither one of those can you do. Okay, questions there? So now that we have all these lovely things here, now we just transfer that to this right here. And we try to look and see which of these that we could use. Could we use this piece divided by this piece equals this piece over this piece? Well, you could try it, but let's look back. What is this little piece right here? It's 1, yeah, because you know the whole thing is 6. So that is 1. So you could do 1 over 5 equals, what's this piece? That's going to be a little bit more tricky, right? We don't know what that is, but then this piece right here is 4 plus x. So you could do 4 plus x on the bottom. There is a way to represent this piece, but good grief. I mean, it's going to take a little bit of work to do that. I wouldn't recommend that way. That is actually step 1. That's this first proportion. So we're not going to use that particular one. That's why I've given you so many over here. So let's try a different one. Couldn't we do this piece, which is 5, over the whole thing? 5 over 6, whoops, over 6, is equal to this piece over here, which is 4 plus x, over the whole thing, which is 12. So that was a version of number, what over here? Which property? Property number 4, right there. Okay, it was just a flip-flop of that, but no biggie. Okay, so now we have our proportion set up. Now, can we reduce any fraction? Doesn't look like it, so we'll just proceed. We'll just cross product. 12 times 5 is 60. You got 6 times the entire thing, 4 plus x. And then, of course, you got to distribute that 6. So, whoops, 6 times 4 is 24. And then 6 times x is 6x equals 60. And then you subtract 24 from both sides. And you get 6x is equal to 24 from 60 is 36. Divide by 6. And you get x equals 6. And there you have it. In this particular case, they didn't ask you to plug back in and find any lengths. If you did, you would just plug it where x is, but they just said, okay, what's x? It's 6. Okay, so remember, apply these proportions over here on the right to when you have 3 or more parallel lines. They'll typically just give you three parallel lines. All right, let's move on to, looks like our last one here. Yes, there we go. You can pause the video. Resume. Okay, so let's look at this last scenario and then we'll be done. It says that if one angle of a triangle is bisected, meaning it's cut into two equal parts. So if you look at this large triangle right here, this large triangle, I drew this little segment in such that it bisected this large angle and I cut it into two equal parts. So I made those two little angles here congruent. So that's the bisected angle. It doesn't have to be the angle down in the left-hand corner. It could be the angle up here, it could be the angle over here, doesn't matter which one. If that happens, that we bisect an angle, it cuts the triangle proportionally. So what happens is, it cuts it such that this length right here, this A, divided by this length right here, B, so A over B, is equal to this length over here, C, divided by this length right here, D. So A over B equals C over D. Okay? Or, if you want to look at it differently, if you want to look at it like this length right here, A, divided by this length, C, is equal to this length, B, divided by this length, D. You could look at it like that, which is our second proportion. Whichever proportion you would like to memorize is totally fine. Both of them will work. Whichever one that you're comfortable with, go to it. Okay? I personally use this one. This first one right here, it's just one that I chose, so whatever. All right, let's take a look at this. Here's your bisected angle right here. So it's going to cut these proportionally. I'm going to use my first one right here. So I know that 2 over 1 is equal to what? 2x minus 4 over this piece right here, which we know is, the whole thing is 3, so that has to be 2 over 2. Now you have your proportion set up. You can cross product. So you get 4 is equal to 1 times 2x minus 4 is just 2x minus 4. Then we just add 4 to both sides. So it gives you 8. It's equal to 2x. Divide both sides by 2. You get x is equal to 4. And there we have it.